This is a story about the universe. But more than that, it's a story about how we came to know the universe. For nearly 50 years, one man, J. Richard Dick Bond, has shaped the way scientists see reality itself. He helped build the standard model of cosmology, not in isolation, but in friendship.
Friendship is what actually drives great science.
But now, as teams grow more massive, theories get stranger, and a new generation loses sight of the why behind the what, Dick Bond fears that we're losing something deeper.
You have to maintain your technical chops, but you also have to be able to see the big picture.
In this conversation, we'll cover everything: entropy, coherence, then the quantum universe, dark energy, the Hubble tension, and what comes next, but never forgetting the forgotten power of scientific friendship. This isn't a story just about physics. It's about the people who dared to ask, what is the universe really made of? And who are we? Those that try to understand and wrestle with it. This is Professor Dick Bond, and this is Into the Impossible.
Dick, it's lovely to have you here at UC San Diego. Thanks so much for coming out and making the trip. I know it's hard to come from Toronto to San Diego in the winter.
It's a tough call, although you haven't made it absolutely sunshiny while I've been.
Well, I've got a lot of questions for you, but the first one I have is this talk that you're going to grace us with later. Tell us about that. Tell us about this wide-ranging talk.
What it is that made what you might call the golden age of cosmology, which I have been privileged to be a part from the emergence in the 70s. It actually emerged in the 60s and even earlier, as you'll hear. But the thing that made all of the work happen and all of the great discoveries is not just an intellectual game. It's the friendships that underlie the interactions of scientists, which caused the creation of this great thing. It was essentially a movable feast of friends going from place to place, all interacting together and developing things. And as we were developing the basic ideas, which have become the standard model of cosmology, in which dark matter plays an extremely important role, and after that, dark energy. But I think I won't be able to get to it in the meeting today, or in the talk today. But I organized a conference that was seminal in the subject of the cosmic microwave background, near and dear to you.
It was
87.
Yeah, before my
It was called Delta T over T, which was a play on the fractional temperature that we're trying to get to in those days and have gotten to with extreme precision. But the second T was spelled TEA because I was in Canada and it was a T thing. But what it did and why it was so interesting is that I used it as a vehicle to bring together, for the first time actually, theorists and experimentalists, because in those days, the people that were into the cosmic microwave background experiment were deep in their labs and they weren't really connecting
That's right.
to the astro aspects, which have now become, totally taken over, but they were into the devices and all of that. And so this was the great day, and I had the wisdom of getting Dave Wilkinson of
My
the
great
Wilkins.
advisor. That's right.
Yeah, he and I basically choreographed this. And so the drawing power of the experimentalist and the theorist was perfect. And to this day, it's remembered as one of the great events. And in fact, I was just at Hopkins a short while ago, and Chuck Bennett comes up and he says, it was the greatest meeting he's ever been at. And it was mainly because it was creating a field and a coherence that hadn't been created before. I mean, there were kind of random associations with the microwave background before, but it was never done as if it was a subject on its own, which is what we made.
You reified it. You made it in reality.
But what it also signaled is that we were trying to tightly couple the theory and the experiment, which is a new phenomenon, because usually the experimentalists or observers would deliver information and then the theorists would play around with the information, but it wasn't tightly coupled.
That's right.
And the history of the microwave background is we made it tightly coupled. So there was a joint work of the theorists and the experimentalists, and what I came to call the analysts, because we spend a lot of time taking the huge data stream that we get and analyzing it in order to draw the perfect cosmic information that we can get from it. And so the whole story in your career, it's all part of that flow. And we're all very proud of what actually happened. The only thing now is that the teams have become so large that it's difficult to maneuver. It makes it difficult for young people to find their way. But the outcome of the experiments has been outrageous.
Oh, yeah.
I mean, it's
incomparable.
It is the golden age of cosmology, without a doubt.
That's right.
And that's going to continue. And I'm sure that people have heard on your podcasts, that Simon's Observatory is on its way to do further miracles.
That's right.
But it's not the only thing. There's a lot of things that are happening, not just in the microwave background, but in the large-scale structure. So the model of the microwave background, where theorists and experimentalists got together, we were also able to inject into large-scale structure observations they were called redshift surveys. And so I must say, a lot of very good friends of mine were involved in all of those transformations. And of course, experimentalists and observers became very close friends.
Yes. It's a beautiful way to describe it. And I remember meeting you 10 years after that conference. You invited me and Peter Timby, who is Dave Wilkinson's star graduate student, in addition to Suzanne Staggs and many others. And you invited us to CETA, the Canadian Institute for Theoretical Astrophysics, some other acronym in French. But I remember meeting this person. I was reminded of the saying. I was a brand new student. I was a student also of Robert Brandenburger, as well as Alexander Polnareff, a great Russian, physicist, and the spirit of Zeldovich. And I remember him telling me that when some Russian physicist, maybe Zeldovich, met Stephen Hawking, they said, or Stephen Hawking met Zeldovich. He said, I thought you were like Bourbaki, like a collective, a pseudonym. I thought that about you. I was like, how's this guy, who would later take us out for beers and to the Toronto Blue Jays, who beat my beloved Yankees, if I recall correctly, from over 25, almost 30 years ago. What is the experimental minimum? Not the theoretical minimum that Leonard Susskind, past guest on the show, has talked about. What is the minimum about an experiment that a theorist should know?
Well, my view is that we are not training very well these days, because everything, by force of advancement, everything is becoming so compartmentalized. And so these great phenomenon, which are these collectives of theorists and experimentalists together, they have a tendency to make the budding young scientists into somewhat cogs in a wheel. So the thing that behooves us is to make sure that, yes, you become focused and you do, the key technical work, but you cannot lose sight of the one thing that impassioned people to go into the subject, which is that you have to have the big picture. And the big picture has to be with you every single day while you're working on this. You can't be, just doing your programming or whatever, because then it becomes quite similar to the kind of work you might do in the so-called real world of Google and other things, who have very, very interesting problems now. And it is essential for us to make our subject attractive. But why do people get attracted to the subject? Is because we ask the big questions. But the thing is, that isn't what you do day to day, or that is a tendency not to do day to day. But I think that we have to get back to a way of rethinking graduate education and postdoc education for that, because I played a very big role with that. That's the future is going to be that we make well-rounded people who can still do the detailed expert things. And you try and do that with the general courses that become somewhat more specific, but there needs to be much more attention to that to make sure that people come out with the ability to look at, the entire story as opposed to the details of one story. Mm-hmm. I mean, often science used to be described as there were a bunch of bricklayers, and then there were the architects, and the architects were the ancient beings in the subject. And I don't think it's that way. It's everybody is making the architecture, and everybody is laying the bricks. And if the architects lose sight of the laying of the bricks, then they have lost sight of what it was that was their essence in getting into the subject. So it goes both ways.
Mm-hmm.
You have to maintain, your technical chops, but you also have to be able to see the big picture. But I think that's everywhere at every level of development, even in reaching into high schools and early university career, that this kind of vision of how to think about life, the universe, and everything is something that science does extremely well, except it's not doing it as well as it should.
Yeah, it's not sustainable, that's for sure. And speaking about, early education, early influences, I recall that you were very heavily influenced by George Gamow and also by your interactions with your advisor, Willie Fowler. And I'd love to talk about those two men and how they influenced you.
You're going to get a blast on that today. And that you bring up Gamow, that is amazing. I don't know how you knew that I'm a Gamow-phile.
Some research. Yeah.
You will see that Gamow plays a role, but I'm not the only one he played a role in. He did the most brilliant, a general book. It was called 1, 2, 3 Infinity. Can you think of a better title than that? It is amazing. And he was trying to do a grand unification in essentially late 40s, early 50s of how you could think about how everything came together from the early universe through to the formation of life on Earth and geology and all of that. And so he was trying to bring everything together, which is, of course, I think what we all are trying to do. But he did exceptionally well. And so, for example, many famous physicists were influenced. If you look at a somewhat younger grouping, they were probably influenced and got into science by Star Trek or something like that. But there were the books from an earlier time that played a huge impact. And the 1, 2, 3 Infinity had a big impact. It wasn't just on me. It was on Glennis Farrar at NYU, but David Gross and I just completely resonated on Gamow. And so you're going to hear this today. I probably shouldn't be repeating it, but I will, because this will leap us into where I am going with my thinking and where I think many people have gone before. Schrodinger wrote a book called What is Life back in the 40s, and it was transformative. It was the reason that physicists rushed into biology.
Yeah,
it impacted Crick and Watson.
Yeah, or physicists.
And it's all about entropy, which is what you're going to hear about today, but it's called nega-entropy. And so, but I won't go too far there. What I will say is the thing that I found that was quite delightful is that Gamow was just this polymath who did everything, but he picked up on the DNA story and organized an entire grouping of scientists, a special grouping of scientists, to talk about DNA. It was like a network. And there was some kind of brown ties or something called themselves.
That's right, the brown tie. Yeah.
I have nothing but admiration for his creativity and his far-ranging ideas. And, Hoyle came up with Big Bang as a bad word, if you like.
Sure, right.
But Gamow was right in the center, but so is Hoyle. I love Hoyle. But Gamow is up near the top. I'm going to be talking about a number of these characters today because they really set the stage. And one of the things, and we're going back now to an early part of the conversation, which is that flow of information and development of it from, let's say, from 1900 on through the quantum development and what they were thinking and how they saw things in the 30s, into the 40s, and into the 50s is something that a lot of people are kind of losing sight of.
Yeah.
And that's a shame because, because if you look at the old papers and the old books, they were looking at things and they didn't know everything, but they were trying to do it and not make statements that were going to be clearly false. But then there was no choice but to take leaps, which they did. And that's what Gamow did. But, you know, he also predicted the cosmic microwave background going back to early.
The student Alfred, right, passed away relatively recently. And then the part of that kind of motivation for the question about, you know, how you train your philosophy of training students to be interacting with experimentalists has always been good. I kind of view you as sort of the theoretical version of our good friend and beloved colleague Lyman Page, who is sort of the counterpart. He's a master of experiment, National Academy.
And one of my best friends.
One of the closest friends to many of us. He's like an uncle. You know, he's been on the podcast many times as well. But I always think he trains his students to also think theoretically and not to do new theories. I don't think my students have to come up with some new theory, but they have to understand that they're at the level of a graduate student, or else they're kind of plumbers. And there's nothing against plumbers. We need them too. But the fact is we can't have people doing stuff and not understanding why they're doing it. And to me, you've always had your why. You've always understood what exactly you're trying to answer. And I think the question that is most an enigma about me is how do you, about you rather, from me, is how do you choose what you do? What's the most interesting topic to you right now? Is it the Hubble? Because you never follow these fads. Even this talk today, which, you know, as the late great Andrew Lang, my mentor, used to say about you, is a talk that, you know, only Dick Bond could give, and sometimes only Dick Bond can understand. I remember you speaking at Caltech when
we shall see if I can do a little bit better in my dotage.
We love having you.
Well, I'm famous for being able to put the entire universe on one slide.
Exactly.
And just riff.
So what is the most interesting in the universe?
Well, it is exactly what I'm talking about today, because it's a grand unified vision of how everything fits together.
Dark matter, dark energy.
Well, all of that fits in, but the basic underlying set of issues are the concepts of entropy and coherence. That's entropy in a coherent universe, but I see it everywhere. But the coherence is associated with organization of counting things. Entropy is about counting things. And the other ingredient that goes into quantum mechanics is phase and phase differences.
Yes.
And the phase is what builds coherence. It can be large-scale coherence or small-scale coherence. And when people think about entropy, they think about random, and they usually think about macroscopic.
Right. Coffee and cream mixing.
Yeah.
You're right.
But in fact, it's actually quite microscopic. And it is the two together that make quantum mechanics. Quantum mechanics is the queen of everything. Everything flows from it. And it flows from those two entities, the entropy and the phase. This is not commonly embraced. It could have been, but it does, you know, and codify itself in a wave function of the universe, if you like. But you can say that word, but that doesn't give justice to the fact that it describes everything, including all of life and all of the ideas associated with humans, that all that has to flow from essentially this quantum thing. And so what I see is that every single aspect of the development of the universe is nicely cast into this framework. And it gives me an underlying vision to try and describe along the lines, if you like, with a little bit of hubris perhaps attached to 1, 2, 3 infinity, where you're trying to do a great leap at the approaching end of my scientific career. When I was young, I thought I should be a writer. I don't like to write that much, but I write to myself all the time. That's my mechanism. But I said, you know, you can't really be a writer without understanding the leading edge of human thought about the universe. And so that was how I decided that physics was the path. But it was always with the view that as one approaches the end, you take a great leap. And the most likely situation is your leap is not going to be accurate. But if you don't do it, then you aren't going to try and have internally in your own mind done an internal unification. And the whole development of human beings is to try and internally unify under hopefully a force for the good arrangement. But that is, you know, what the development of a human is about. It's to have a a coherent view in which all of the little entropic, if you like, little fluctuations that go on all the time in people's brains are somewhat transcended, and you can see things in some relatively clear way. So this is a non-trivial thing, and it could be that the universe is all about a big cosmic joke, or it could be a simulation, or all of these ideas are possible. And but we have to proceed as if the science of reason, which is really what we're doing, reasoning about things in the universe, that's something that is actually giving you answers, as opposed to it being you're going off and planning.
And actually, one question I alwaais get from my audience is, why don't you push back on these theorists like Neil Turok? And I do, and it's always with love and respect. But the fact is, for lay people that do watch the podcast, I mean, we have Nobel Prize winners and we have high school students. But the point is, when you hear about so many speculative things, wormholes, black holes, time warps, traveling black holes, dark energy, dark matter, and then the popular trope is, well, how can we trust you guys? Because you don't know what you say. You don't know what 95% of the universe is, and that you're going to speculate about how time travel and string theory and brains and M theory and all these things can revolutionize physics and give us the future that we all love and deserve. How do you push back on that? The notion that what you do as a theorist is often, or your fellow colleagues, if not you, is not as often grounded in the cold, hard experimental reality that's at least falsifiable.
Well, you're bringing up an interesting point, which is that you aren't, but I'm going to pretend that you did.
Yeah, okay.
I do not like when colleagues I know very well, but their basic thing is to learn something and then immediately turn around and try and become the high priest delivering information to the masses. Whereas if you're a scientist and a true scientist, you have to be incredibly humble about not knowing, and that it's a process where you're trying to know, but you don't have the audacity to say, I know the answer. You say, this is, where we're at now. And I think that in terms of delivering information about science to the public, a little more humility is important. I mean, I understand the reasons for, trying to speak with authority, but I think what's more important for the lay public to see is that the scientists are struggling just like everybody else with answers of, the reason for being and all of that and how it fits in. And it is not good to try and say, well, I know, and I am going to deliver the cosmic truth to you. And I hope that I will tickle imaginations today with the idea set, which I think is really good, if I do say so. But it is hopefully what it's going to do is to trigger people to have, these synaptic gap explosions to try and make their own connections, because nobody is ever going to make the same connections, which is the way of science. Everybody is following a path, and the paths have a correlation or a coherence among them, but they're different. And so everybody's unification internally is different, and you have to respect that. I mean, it's also true that, I'm sure you've seen it. You get these things from what we used to call cranks who would, I have a theory. My theory is the best theory.
I plan on it. Yes.
And so that's another example of someone who is trying to understand, and that's admirable. But then before they've actually understood, they say, I'm going to deliver things so you can all applaud me. I just don't like that attitude.
Yeah, I agree. And there's also an arrogance about, first of all, it takes chutzpah, it takes arrogance, a little bit of moxie to confront. After all, our enemy has an infinite amount of resources, Mother Nature. She's not running out of troops to assail us anytime soon, right? We're waging this infinite war against an army that's always in retreat. But it's possible to make progress. And I think some of that comes from having, gumption. So on one hand, Einstein would say things like, if the 1919 eclipse survey turned out to not demonstrate the deflection of starlight, well, then I would feel sorry for God because my equations are right. On the other hand, he would say, I am supremely stupid and I know nothing. It's just I know that I know nothing, sort of summarizing that. Or Feynman would say things, you probably ran into him many times, and he would say things like, if you can't explain it to your grandmother, then you don't really understand it. And then when he was asked by the Pasadena Star News the day he won the Nobel Prize to explain it, he said, "Look, pal, if I could explain it to you, it wouldn't be worth a Nobel Prize, would it?" So how do you balance this? Seiberg has said things like, if we discover something that's not consistent with string theory, we'll just call it string theory. How do you reconcile the arrogance, but the balance between arrogance and humility that you display, but so many of your theoretical counterparts, sad to say, do not?
Yeah, I'm not sure that I actually really like the people that we've been talking about.
Yeah.
Feynman
yeah.
was outrageously interesting, but I'm going to extol today the incredible virtues of his thesis advisor, John Wheeler,
right?
And Bohr also playing a big role in the story of today.
Mm-hmm.
But Feynman I did know, and he was fantastic. And the thing that what you would like for people to see, and people did see or hear, how the mind is operating to the extent that you aren't looking into it, but you're just seeing. So I'm going to tell, I don't know why, but I'm going to tell a little tale about Feynman, because I was.
And I have to hear about Fowler too.
I was a Feynman scholar at Caltech, and so I met with him on a number of occasions, and he taught me an advanced quantum mechanics. It had a big impact on my way of thinking because it was a very natural way of thinking, and it was irreverent. And the irreverence was what you really need in trying to deal with Mother Nature, who doesn't necessarily applaud your irreverence, but it's the best way to approach it. I started in supernova, and it was because neutrinos, which are, some of the fundamental particles that equivalent of photons in many respects and gravity waves. So as an expert in neutrinos and gravitational collapse that ultimately produced supernova, and Feynman was going to give a talk to Boy Scouts of all things in Pasadena. So he had me come over in order to core dump what I knew about neutrinos and supernova, because that was one of their most important applications. I gave him this spiel. I think I thought I was somewhat clever in those days, but I was still with humility, especially if you had the
scale it to the Feynman standard, right?
Yeah, well, if you've had the great
experience compared to Feynman,
the great experience of seeing Feynman and Gell-Mann in action on a daily basis, then you learn humility just from that.
That's right.
But in any case, so I give him this whole spiel about gravitational collapse and how it was all working and that. And we had, kind of fooled around with the multidimensional aspect of it. But he sort of looks off into the distance, but you can see he's looking at a whole landscape of action occurring in his mind. And he comes back and he says, Rayleigh-Taylor instability. And then within a year, Rayleigh-Taylor instability became the subject in supernova theory. So, and, how did he get there? Well, first of all, he had spent a lot of time looking at turbulence in the 50s, but also they all got schooled in Los Alamos with the development of the bomb. Not just him, Beta, and they were all doing incredibly practical things in terms which were really great for the development of astrophysics and cosmology, because it was, applying some of the methodology of things that go bang in the night to science and to the universe at large. Anyway, he comes back, he says this. So I go back to Fowler, who's my thesis advisor, and I say, I got to drop everything and work on this. And he says, finish your thesis, which I did.
Sage advice. What was your thesis topic?
It was, you'll hear, it was gravitational neutrino transport during gravitational collapse. But I got a report You're going to hear rather too much about all of this because I'm going back to my core. And I'll tell you one of the reasons for doing that today, but I've been doing it because it's going to be hopefully this book that I get around to writing. George Fuller, faculty member here, great guy, Mr. Neutrino. He was Willie Fowler's last graduate student, and I was his second to last. So we knew each other there. We didn't work together. We're now working together, which is a fantastic kind of grain unification in life. But he also got into the entropy game, like I did. Well, anyway, the bottom line is that he was a Mr. Supernova as well. And that's essentially, in a very broad way, it's what his career has been. And I have gone all over the map, but with always this sort of underlying grand unified way of looking at things, which is an entropic view, as will be described in more detail today. So trying to come up with a way of looking at things, which is been to me a pleasure, because every time you have a new idea, it's incredibly pleasurable. And the problem with science is you say, yeah, but everybody knows that, which is not true, it turns out. But it's because if you can actually really get at an idea, then it looks like it's simple, in spite of the fact to get to that idea was not a simple path. But it then becomes, and so the mantra now is, well, it's all just quantum mechanics. Yeah, but Feynman, and we go back to him, once was quoted as saying, nobody understands quantum mechanics. Just like I said, von Neumann said, nobody understands entropy.
Although your fellow, well, he's Caltech undergrad, I believe, Stephen Wolfram says he now understands entropy. He now understands both quantum mechanics, time, and entropy.
Well, maybe he's come up with the same ideas I have.
He might, yeah.
I don't think that's true. I actually, of course, overlap with him at Caltech, and he had worked on before he became Mr. Mathematica. He worked on baryogenesis, which is trying to understand why there's more matter than there is any matter, which is a very subtle issue. And then I did some work on that as well, relatively early in my career, but I enjoyed it because I learned a lot from it. Anyway, so that was his development. And then he was into relating computers to particle physics. And that means that you are thinking of information at the same time as you're thinking of field theory. And my contention is, like Wheeler, who I'm going to quote today, is that everything is information, that is the nature of physical reality, which is, if for bit, well, it's more than that. It's more than that. It's just interesting that, we're all thinking of solid things, but in fact, it's almost like condensed information. That's the way to actually think about the universe at large. It's an uncommon view, but it's actually very deep, because what it does, it brings information into the absolute forefront of one's thinking about how things develop, which allows ideas to emerge, just like everything else may have emerged, but complex ideas which have a coherence. Again, we're back to the word coherent. Anyway, so
that's what's called a teaser and foreshadowing.
I don't want to give my talk.
No, we're going to record that, and that'll be released, and we'll certainly do that. But I have to be a good host, and I have to ask the hard hitting questions. So one of the questions that's hardest for me to kind of wrestle with has to do with the multiverse. There's a book over there from Fred Adams. You probably collaborated with him, as George has, or at least run across him. And he has sort of this preternatural gift for explaining away some of the most interesting and devious, problems in science, including the fine-tuning problem and other things. But in particular, this obsession with the multiverse. What do you make of it? What is your take on the multiverse?
Well, I am going to talk about that. So I have been dealing with those issues since the mid-'80s. In particular, once we did something that people are embracing more and more, what we did on what was called stochastic inflation, which was a way of understanding how you could create a universe that was arbitrarily large and possibly eternal, although you will never be able to know it's eternal, because if it's semi-eternal, you don't know where time zero is. And so you're just looking at sections. So you never know whether it's going to be eternal or not. And I actually don't think that eternality is probably feasible, but you cannot, as you said, you can't tell Mother Nature what to do. She knows. Yeah. But anyway, so for me, the multiverse is actually one verse. It is the universe that is interconnected in its way. And the interesting thing and this is controversial, the way quantum mechanics works is that if you try and concentrate something too much, then it spreads it out. And it spreads it out according to what is called the uncertainty principle. It turns out to be a very general concept that's operating everywhere, which is not that much appreciated. Everybody thinks, oh, it's only the smallest scales, but it's not true. It's everywhere. And I will say something about that perhaps. But the concept is that somehow the realizations of the universe know about each other. They have kind of make what in the trade is called an effective potential, or multiple effective potentials, that essentially try and channelize where the realities flow. So this goes back.
How do you mean? What do you mean by realities? Oh, is that
so the
choice experiments?
The reality. So an ideal reality, of which probably cannot be attained, would be to have the kind of reality that you always thought reality might have been, which was that everything is classical and it is perfectly determined, and it is essentially a space-time manifold where the space could actually be quite large. I mean, it doesn't have to be 3 dimensions. It could be multiple.
Is it a Hilbert space or a real space? Like 3 plus?
I'm talking about a real space right now. People don't usually think about that in the quantum level, because what the quantum level is actually doing, it is saying I've got probabilities of these realizations, and that it almost thinks that the realizations aren't real, but they could be. But the main thing that what the equations of quantum mechanics show you is that if you try and concentrate information, then the information will spread. And so a classic example of that is the hydrogen atom, where instead of having the electron on top of the proton, if you tried to do that, it would immediately respond. And what you would get is the atom in a ground state or in an excited state. But the main thing is that it's got a scale associated with it. And that scale is associated with the uncertainty principle that you cannot localize that well. But what does that mean? Does it mean that it was never localized? Or does it mean that it's a probability of this happening, that happening, and then the collective average is the non-localization? That's the standard view, if there is a standard view of quantum mechanics. But then the question is that real or not? And then another aspect to make it even stranger is that if I view the wave function as a function of these quote unquote realities, and the realities are kind of interactive. I mean, is if you deal with a wave function psi of x, where x is a position, what is the x? And you have an x here, an x here, an x here, and an x here. And what is describing it is an ensemble of possibilities. But we're used to dealing with this all the time in science, ensembles of possibilities. But the question is whether that interaction is a real thing, or whether it's just that somehow we don't understand what's going on with the quantum mechanics. But the fundamental equation, Schrodinger's equation, says that there is a effective pressure, it's often called the quantum pressure or quantum potential, that is a force which is beyond the usual classical forces, that's responsible for spreading things out. And that's actually part of the equation. It's a real force. But the way quantum mechanics is taught, the way physics is taught, is that it was all because of its historical development. Whereas if we were really clever, we would have started with the wave picture of the universe and then worked our way backwards and gotten classical physics as an approximation to it. But of course, that's not the way it occurred.
Right.
But trying to break people's minds out of, that it's all classical, and then you go into the quantum realm, rather than the quantum realm being the only thing there is, and that the classical is basically limiting behavior. That's uncommon. I think it would behoove, and you'll hear that, I think it would behoove us to all look at it differently, look at it the other way. And I think Feynman was sort of on to that, right? He said it's all, basically did say all quantum mechanics, even though nobody understands. His classic dictum was shut up and calculate, as opposed to try and understand metaphysical things about the physics.
If we had, kind of to select top, 2 or 3 greatest hits, without the fact that you're so, kind of preternaturally, immune to following trends, and in fact, setting trends is more your forte. I see now a lot of trends, Hubble tension, as I said, multiverse, as well as things like, speculations on the nature of dark energy. Because you're so integrated, tomorrow's a huge day in your career. It's a release of ACT data, public data release. So you played a huge role in the ACT experiment for 20 years plus. Tell me, if you could address 1 or 2 of those topics, multiverse, dark matter's nature, dark energy's evolution, the unknown candidates for dark matter as another choice, leaving aside the thermodynamics and the stuff you'll talk about later. Classical astrophysics controversies that we see now. Steven Weinberg once said, physics is short on crises. Well, not anymore. That was back in the 80s. What's the top crisis, and what's the worst trend that a young theorist could be sucked into, that you could potentially avoid them suffering the fate of trend chasing for its own sake?
I think it's inevitable that people will do trend. I mean, that's the nature of theorists, unfortunately. Yeah. And then the issue is, do they have good taste or do they not? But, there is the big pressure to get stuff out.
That's right.
So I'm going to talk in passing today about another way of looking at field theory and the universe at large, where the fundamental ingredient is scale factor, which is a tensor. It's got anisotropic and isotropic things, and its derivative basically is the Hubble tensor. Hubble's tensor, which is a function of not just positions, but positions in fields and time, and that is a description of the gravitational underpinning of things. Why am I going on that little loop? Because I think it gives people a way to intuitively grasp what is actually going on with particle physics, because it's all about strains and strain rates, which are called shears, and that the possibility that there's anisotropic, it's just that it's being done in a larger space, which is multidimensional. So, we deal with the 3 plus 1, 3 plus time. I'm going to sing the virtues today of something that is controversial, imaginary time, but there's also more dimensions to generalized space, manifested in string theory, which is, we're back to string theory. So while everybody else has been abandoning string theory, I'm embracing it. It's ridiculous. But from a much more intuitive way of looking at, I think, so that's why I'm, pinging my ideas, with people like, Lenny Susskind and, the people that are deeply on the edge of thinking about the way information is working with quantum mechanics, which is a major, major, major topic. Anyway, what I see is, great grandification. This is taking this a little bit away. We did multiverse, which, I think about in my own way, as you'll hear, but Hubble tension. So I mentioned that I was in Hopkins. Of course, I sat down with Adam Rees, who has the view, and asked me, of course, what I think. Because unlike some of my friends, you approach things in a somewhat conservative way, but you need a radical element if you're going to do something interesting. And so to me, if everything is described in terms of an anisotropic, inhomogeneous Hubble tensor, then, and that's everything. Well, it is quite possible that you have a big change, especially once you're entering the era in which the dark energy is started to dominate, which is like redshiftless and around 0.5 or 0.7 or so. So above that, it's, like the cold dark matter dominated universe. But below that, you have all of this slowing up, but with an ingredient that we do not understand at all. Our view is that it's related to the vacuum. But as I emphasized to Adam, it is all a phenomenology. It's not
a
fundamental theory that we have, but it is how you learn about it. And you look at it with great respect, because to try and get, a whole Hubble parameter thing, which I am contending is the way to look at everything, is any information you can get about it, especially on the largest scales, is fundamental. And we're kind of not confused, but we're overly thinking about the isotropic component and that it's only time dependent, but it isn't, because time and space are intermingled.
Yes.
Which means that if you are going back to redshift 0.5 where there are changes, then you're also going way out in space. And so the question is the change actually spatial, or is it timed? Or is it associated with, well, there are many things. It could also be associated with density, which is actually what I think it might be, which is that as the universe expands, the density falls. And if the density falls too much, you can have different physics, which is going on. It's associated with in dark energy theory, it's called screening. And our galaxy is supposed to be screened and give you kind of normal physics. But if you go outside of the galaxy a long way, where the densities are quite extremely low, then you can have a modification. For example, one way to look at it is going back to cold dark matter. The cold dark matter could be changing its form in the extreme void regions. But it would be a late phenomenon. It wouldn't be an early
And
phenomenon.
that would change the equation of state. And
Yeah, but it's not a phenomenon that would occur when the density is too high.
is this what Penrose calls error bonds, or is it related to these? Okay. Okay.
So I should also describe something else, although I should be up on everybody's literature. I like, as Feynman did, the pleasure of working things out myself, so that you enjoy the experience of coming up with things, even if other people have thought things, because you know that one way or another, you could make a connection to everything that everybody's been thinking.
That's right.
That's just the way of, the time becomes right to think certain thoughts. But no, so I have not paid, in spite of the fact that I have great respect for Penrose, I don't pay that much attention. He made a misstep in his career, which might not have been a misstep. He got completely enamored with a theory and then said, there are these entities that come from quote unquote before the Big Bang. I don't know did you get him on here?
He's been on many times, yeah.
Well, he's probably riffed about that.
Oh, yeah, many times.
Did he riff about consciousness?
Of course, yeah. I had on the collaborator Stuart Hameroff, who was inspired by his book, his book, An Emperor's New Mind.
Yeah, right.
To write him, and that launched their career.